Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on August 5th, 2025, so about a week ago. This paper shows that the emergence of so-called massive activations, which are key internal values in a transformer that become orders of magnitude larger than normal, is not a random artifact of training. Instead, it's a predictable phenomenon rooted directly in the model's architectural design. The paper is titled, Hidden Dynamics of Massive Activations in Transformer Training, and the implications for model stability and training efficiency are really significant. So to kick things off, this first figure illustrates the scaling relationship between a model's size and the magnitude of its massive activations. The plot charts the number of parameters against the maximum activation ratio. We see a steep climb in this ratio as models grow from 14 million up to 1 billion parameters. Then the trend plateaus for a bit before rising again in the very largest models. This pattern suggests that massive activations emerge gradually and predictably with scale, rather than randomly. Alright, these next plots give us a fantastic before and after snapshot of this process. The top row shows 3 different models at the very start of training, and you can see the activation values are low and fairly uniform across all the layers. But now, look at the bottom row. This is after 143,000 training steps. The change is dramatic. The top activation magnitudes have exploded, and distinct patterns have emerged, with peaks appearing in different layers depending on the model's size. This clearly shows that massive activations are learned phenomena, not something present at initialization. Building on those observations, the researchers proposed a mathematical function to describe these activation trajectories. This table then details just how well that function fits the real data. It shows the average R-squared scores across layers for each Pythia model size. R-squared is a statistical measure of fit, where a score of 1 means a perfect match. And as you can see, the scores are outstanding, generally above 0.98 for models over 160 million parameters. This confirms the evolution of massive activations is highly predictable. So what do these predictable patterns actually look like? These heat maps visualize the 2 main behaviors across different layers and model sizes. The plot on the left shows activation magnitude, and that bright yellow band clearly indicates that middle layers consistently have much larger, massive activations. Then, the plot on the right shows timing. The darker colors in the shallow and deep layers mean they peak early in training. In contrast, the bright yellow middle layers peak at the very end, showing a continuous, logarithmic rise. To give you a closer look, these plots show specific examples for a shallow, middle, and deep layer in 2 different models. The top row shows examples from the Pythia 1b model, and the bottom row does the same for the much larger Pythia 6.9b model. You can see how the same simple mathematical function, shown by the orange line, beautifully captures both the early peak and decay pattern in the shallow and deep layers, and the steady logarithmic climb in the middle layers. The fit is just remarkable. So the big question is, can we predict these mathematical parameters just from a model's architecture, before training even begins? This table shows the results of trying to do just that. It lists several machine learning models and their R-squared scores for predicting each parameter. The key takeaway is that some parameters are highly predictable. For instance, the asymptotic baseline, K, which sets the final steady-state magnitude, is predicted very well by an XGBoost model. And peak occurrence, lambda, is also strongly predictable. So wrapping up, the key insight is that massive activations are not random training artifacts, but are instead predictable and even controllable through architectural design. This opens the door for building more stable and efficient models from the ground up. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.